Okay, welcome back, ladies and gents, to our final video in topic 2.7. This is all about VSEPR theory. VSEPR stands for valence shell electron repulsion theory, and we can use this to help determine or make estimates about the shapes of molecules in three-dimensional space. If you take a look at this model right here, I have a purple central atom, and then bonded to the edges are two white atoms, or also known as electron domains. We call those electron domains because they are involved in a bond. If I try to distort this model and move those electron domains too close to each other, you can see that the molecule immediately corrects itself because of the repulsive forces between those two electron domains. Remember, electrons are negatively charged, and when two like charges get near each other, they repel. Watch what happens when I add another electron domain. Watch what happens to the shape. Right now, the shape is a straight line, but if I add another domain, the shape becomes triangular, and you can see that the two white electron domains shift downward due to the repulsive forces between those domains. Coulomb's law can explain this very well, ladies and gents. Remember that Coulomb's law says when two like charges get near each other, they will repel. Furthermore, or more specifically, the repulsive forces between the like charges are decreased the further away that those like charges are from each other. Okay? So, these two electron domains are as far away from each other as possible, but when you add a third one, they will move even more to ensure that all three of those electron domains are as far away as possible, thusly minimizing the repulsive force between them. And remember, all atoms want to reduce the repulsive force between them while maximizing attractive force. If I add another domain, you can see that the shape changes even more. Okay? Let's go ahead and go over a few examples and notations on how to exactly determine the shape of a molecule in 3 dimensions. And in order to do this, you're going to need page 6 of your AP reference packet. Page 6 includes the VSEPR theory chart. And on this chart, we need to focus on 3 columns. No, actually 4, now that I'm looking at it. We want to focus on the bond angle column. We want to focus on the geometry of the atoms column. Don't focus on the geometry of electron pairs. We don't want to look at that. We want to focus on the geometry of the atoms column. And then we want to look at the type over here, all the way over on the right-hand side. The type is a special notation that we use in order to match up the notation with the actual shape, and we'll see how to actually write those notations right now. Okay? Alrighty. Let's take a look at a molecule, CH3. I'm sorry, CH4. Okay. We need to determine what the molecular shape of this molecule is with respect to the central atom, which in this case is clearly C, carbon. In order to do this, we need to write the type notation. And the type notation is made of a series of A, B, and E letters. A stands for the central atom, and every time we determine the molecular shape of something, there will always be an A letter because all of them have to have a central atom. B stands for the number of bonded domains. Or in other words, everywhere that you see a bond. E stands for the number of lone pairs. Okay. And when we're looking at the number of lone pairs, it's the number of lone pairs on the central atom only. It's the number of lone pairs on the central atom only. Alright, let's go ahead and write a type notation for methane here, CH4. The central atom is C, so automatically we have an A in the type notation. Then we need to look at the number of bonded domains, or how many things are actually bonded to that central atom. Well, I have a bonded domain here, a bonded domain here, a bonded domain here, and a bonded domain here. That's 4 bonded domains. So this is AB4 so far. Now let's look at and see if there are any lone pairs on the central atom. And if you look back there, you can clearly see that there are no lone pairs on carbon, because in AP chemistry there should never be a lone pair or any unpaired electron on a carbon. Okay? So our type notation is AB4. Let's go back to our VSEPR chart and look up AB4. And if you look up AB4, we can see that the geometry of the atoms is tetrahedral, okay? And it has a bond angle of 109.5. So this shape is tetrahedral, and the bond angle between these hydrogens here is 109.5 degrees. Let's take a look at the, methane in the simulator here and confirm that. Okay, here's methane, CH4. The 4 white domains are hydrogen, and then the gray one is carbon. If I click show bond angles, we can see that the bond angles are 109.5, and if I click show molecular geometry, we see that it's tetrahedral. So if we could go down to the molecular level and look at methane, we would see a tetrahedral shape. These shapes, ladies and gents, do determine the chemical properties of the molecules, but we won't get too much into that for now. Let's take a look at another example. Let's try ammonia, NH3. And I'm hoping that you see that in order to determine these shapes, you do have to write a Lewis structure. Okay, taking a look at this one, let's start with the type notation. The central atom is obviously N, so that's going to be A. Now, let's take a look at how many bonded domains do we have. Well, there's 1 bonded domain there, 1 bonded domain there, and 1 bonded domain there. That's 3 bonded domains. So far we have AB3. Now let's look back at the central atom and see if there are any lone pairs. And in fact there are. There is 1 lone pair right here on the nitrogen. So this is ABE. There's an implied 1 here, but we don't have to show it. So the type notation is ABE. Let's go back to our VSEPR chart and see what shape is associated with AB3E. Excuse me. AB3E. Yes, AB3E. Okay, AB3E. It's right there. It's 1, 2, 3, 4, 5 down. And the shape of this molecule is trigonal pyramidal with a bond angle of 107.5, give or take maybe a few degrees. So this is trigonal pyramidal. And this bond angle here is 107.5 degrees. Let's verify that with the simulator. Yep. Now this one's saying 107.8. Remember I said give or take maybe 0.3 of a degree because everybody's figures might be a little bit different, but it's well within the margin of error. And we can see that the molecular shape down here on the lower left-hand corner is in fact trigonal pyramidal. Okay, ladies and gents, that is the basics of using VSEPR theory and type notation in order to determine the shapes of molecules and determine their molecular geometries. What I'm going to have you do now is work through a few sample problems coming up on the following slides, and then we will discuss this a little bit more in depth during our synchronous time.